আচ্ছা ঠিক আছে, so maybe we can start. Okay, so hello and welcome. It's not figured. Okay, like it's a fashion. Okay, I think now we can start. So hello and welcome everyone to the final colloquium before the break. So we meet again after the break. And this is a real pleasure to have with us Dr. Chowdhury. And Dhruba happens to be our alumnus. And so he got his undergraduate degree from Residency College. I think she was the alumnus from the last batch of Residency College in Harvard University. He got his bachelor's in 2013 and then came to our master's program and joined Residency University for the master's program in 2013. And 2013 is the time when we revised our curriculum and started a new curriculum. So that's when we introduced 2020 master's physics component. So Dhruba and for our paper and our people were the first batch under the new MSc curriculum. And so Dhruba was one of the first students who worked fantastically and took real advantage of the 2020 thesis program. And then finally, because we pushed, we published a paper from his thesis in the Statistical journal, and that is, as I think I have already advertised, my first paper with Residency students. So Dhruba is always very, very special and dear to my heart. Now, then, after so we waited for 1 year, fellow working with things that was talking about it. And then in 2016 August, Dhruba went to Yale for his PhD and defended his thesis in August 2022. And now we are very glad to have him here. He will be joining Professor Abhishek as a Prize Fellow since October once he gets to Dutta. Dutta is still happy. So that's a great opportunity that we will have him. And he did some fantastic work in his graduate school. And you're going to hear about the constraining dark matter with gravitational heating and accumulators. Just one anecdote about Dhruba, I would say that I've seen a lot of students these days, particularly, in fact, yesterday, a student came and told me that, oh, pursuing to admission into our nursing physics program, and who was saying, oh, I'm actually also তো কোনখানে আমার একমাত্র ছেলে আমি যদি বলিও কলকাতার বাইরে আমি তো কলকাতার বাইরে যেতে পারবো না প্লাস অলসো উই ওয়ান্ট এখন চাই যে একটা সিকিউরিটি চাকরির কথাটা চিন্তা করতে হয় and then I gave him the example of Dhruba, and I'm taking the leader to share the story. So Dhruba too, you are such a brilliant person, and let me give you another anecdote that based on his question, one of his questions in my cosmology class, I actually framed one problem in the final exam. If you ask such a brilliant question, that was actually written in your reference letter. That was sent again. Okay, great. So then he was two months, or in fact like that. He was saying, oh no, I don't know what to do. Maybe I'll go and do this and that. And once it could be mentioned, you are taking the mission to get him to sell that story. Once he told me, I was, my dad, and all that stuff. I'm thinking of teaching. I love teaching. So teaching at some PG or something. I was like, what? Like PG. And then he said, how because you are, they actually pay handsome, like saying, so this is a foreign going to be actually the legislative funding. Instead, so hearing that, that's why I wanted to write the paper for the Dwarf. And then, so that's what I want to say, all of you are young people here, that yes, we do have constraints in life, and we really don't sometimes understand that how can we expand our horizon, but always keep an open mind, because we never know what's going to come to our plate tomorrow, and definitely we don't know what's going to come to our plate 2 years later. So once you get older, you will see that there will be lots of constraints already. I cannot do the things that I could do when I was 20 years old. So I would tell all of you, and I see a lot of new faces here, more of you that keep an open mind. Enjoy what you want to do. Enjoy life. Enjoy what you want to do. Don't do things because someone forced you to do. And always keep an open mind and keep your horizon. Without further delay, let's welcome Dr. Chowdhury, and let's hear about her.
Hello everyone. So thank you very much, first of all, for inviting me. It's always great to be back at presidency. I was here in 2016. No, I was there in 2019, 3 years ago, and so I'm back here after 3 years. So it's a great feeling. And thanks, Christina, for the kind introduction. I will also take this opportunity to definitely say that the research component of the master's program was great. If it was not there, I would probably not have been able to go to Yale for my PhD. So it was really a big platform that I got. And of course, all the faculty at presidency, Mr. Rexina, others up here today, they helped a lot. And I was very thankful to all of them. So with that, I will begin. So the title of my talk is Constraining Dark Matter with Gravitational Heating and Cooling Processes. Okay, so let me begin with the this is a distance thing. You need to point in that direction towards the laptop. Yeah, I'll just use the laptop.
Yeah.
Yeah. So let me begin with the outline to my talk. So I will start by introducing what we call fuzzy or ultralight dark matter. So something different from what we all learn in undergraduate or master's courses. What we learn is cold dark matter, which is the most popular dark matter model. So I will not be talking about cold dark matter. I will be talking about a different dark matter model. I will briefly talk about the gravitational heating and cooling mechanisms that are going to be of relevance to us for this talk. And then I will move on to discuss the sources of heating and cooling in fuzzy dark matter halos. And finally, the impact of these heating and cooling processes on nuclear objects, by which I mean black holes, supermassive black holes, or star clusters at the centers of a galaxy, and also on dwarf galaxies. And if there is time, I will also briefly talk about another work that I have done, which is regarding the galaxy NGC 1052 DF2. Okay, so let me begin. So we know that there is ample evidence for the existence of dark matter. We know about the galaxy rotation curves. To explain them, we need dark matter. We know about the cosmic microwave background. We also know that to explain the redshift zero structure formation, dark matter is essential. But then the basic properties of its constituents, for example, what is the mass of the dark matter particle, what is the nature of dark matter, that remains unknown. So here is sort of the region where the dark matter particle mass can be. So it could be a weakly interacting massive particle, which is the cold dark matter candidate. In that case, it would be somewhere here in terms of mass. However, it could also be much lighter. It could be a QCD axion, in which case this is where the particle would be. And also it could be much more lighter axion-like particles, about 10 to the minus 22 to minus 20 electron volts. So these are all the different possibilities that can happen. But there are some things that we do know about dark matter. And one of the things that we know is the dark matter density in the solar neighborhood. That is about 0.5 gigaelectron volts per centimeter cube. Now, given this information, we can ask this question that, okay, what is the interparticle separation? So what is the average separation between two particles such that what is the mass of the dark matter particle at which the interparticle separation is less than the de Broglie wavelength? And by de Broglie wavelength, I mean the Planck's constant by the mass of the particle times the typical velocity. So here is a cartoon that illustrates this. So this is the de Broglie volume. And I'm thinking of a situation where there are many particles inside the de Broglie volume. So if we do this calculation, assuming a velocity of about 200 kilometers per second, which is sort of the typical velocity in the Milky Way, if we do this calculation, turns out that the mass is about 30 electron volts. So therefore, if the dark matter particle mass is less than this, then the dark matter particle will behave as a wave. So that is when we say it's wave dark matter as opposed to particle dark matter. And if it's very light, so if it lies in the region of like 10 to the minus 22 to minus 20 electron volts, then we call it ultralight or fuzzy dark matter. So what are some of the motivations for considering? Yeah.
It's still massive. I think if I think of the mass, it's bigger than that. But it's still low mass. If I think of like particle, that's really large.
Really large. Yeah, so really small. Yeah. Why would they? Because it's the, but their velocities are still.
We are using
right? Non-relativistic momentum, yes. And so what I'm talking about is everything.
I don't know, maybe still the
Thermal, yeah. So right. So what I'm talking about is all assuming non-relativistic physics. Okay, so what are the motivations for assuming this kind of a dark matter model? So there are some problems in cold dark matter, problems in quotes. I'll explain why.
So these are what we have been calling as small scale problems in cold dark matter for a long time. And I will just give two examples. So one here is the missing satellites problem. So what you see in this picture here is the known satellites of the Milky Way, the satellites that we so far have found out. And what you see here is a cold dark matter simulation of a Milky Way-like halo, where you see that there are many more substructure or subhalos. So these are what are the subhalos inside the Milky Way halo. So this is what is known as missing structure problem. So we have many more subhalos, at least an order of magnitude more subhalos than the observed number of Milky Way satellites. And the other is what we call the core cusp problem. So if we look at cold dark matter only simulations, then we see that dark matter halos, they have a cuspy profile. So that means that in the central region of the halo, the profile goes as 1 by r. So there's a divergence at the center. However, if we look at observations of galaxies, then we see that at least some galaxies or a significant fraction of dwarf galaxies, they have cored dark matter profiles. So that is what is illustrated here. So core means that the dark matter profile becomes constant, or it flattens out towards the center of the halo. So that is what is illustrated here. So this is the rotation curve that you would expect from an NFW-like profile. And what you see, these data points, these are data of different dwarf galaxies from the THINK survey. So this rotation curve of gas in dwarf galaxies. And it is better fit with a core profile. So Burkett core, if you take that, then the data is fitted better. So now within the cold dark matter paradigm, there are ways to solve these problems. So, and that is by invoking baryonic processes. So if we take into account baryonic feedback, so feedback from supernovae, then it has been shown that dark matter cusps, they can get converted to cores. And the missing satellites problem, that can be explained in cold dark matter by invoking reionization. So reionization suppresses galaxy formation below a certain so reionization suppresses galaxy formation below a certain mass threshold, and that can lead to less visible galaxies, whereas you still have many more dark matter subhalos. Now, so there are ways to solve this in the cold dark matter paradigm, but then the cold dark matter particle, that has still not been detected. So WIMPs have not been found, and WIMPs are motivated from supersymmetry. There is also no evidence for supersymmetry. So therefore, it is always good to think about alternative dark matter models. Maybe cold dark matter is not the right model of the universe. Maybe it's something else. So in fuzzy dark matter, the way, so in fuzzy dark matter, the way these problems can be tackled is that in fuzzy dark matter, because there is quantum interference, because the dark matter particle is behaving as a wave, then because of the Heisenberg uncertainty principle or the quantum pressure, there will be a mass scale or a length scale, equivalent length scale, below which structure formation will be suppressed. So that can lead to fewer subhalos with regard to cold dark matter in comparison to cold dark matter. And as I will show later on, that in fuzzy dark matter, we naturally get cores in the center of halos. So when we solve the equation of state or the dynamics of fuzzy dark matter halos, then it turns out that we get a core in the center. So therefore, these are the ways in which these problems could be solved in fuzzy dark matter. So that is the motivation why we are thinking of this kind of a dark matter model. Okay. So in the non-relativistic limit, the dynamics আমার হাত লাগছে আচ্ছা 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 okay okay. So in the non-relativistic limit, the dynamics of fuzzy dark matter, that is governed by the Schrodinger equation, and this is the Schrodinger Poisson equation. The first equation, that is the well-known Schrodinger equation. So psi is the wave function. So halos in fuzzy dark matter, they are characterized by a wave function. So this is the Schrodinger equation. So here you have the wave function psi, and here is the potential phi, and mb is the boson mass, so the mass of the dark matter particle, and the potential that is self-consistently derived from the Poisson equation, right? So here you have mb times the wave function squared, that is the mass density, and this mass density gives you the potential. So it's a self-gravitating system where you're solving the Schrodinger Poisson equation. And it turns out that if the mass of dark matter particle is about 10 minus 22 electron volts, then the de Broglie wavelength, that is about a kiloparsec. So which means that if indeed dark matter is fuzzy, if indeed it is made up of this ultralight particles, then that is going to have astrophysical implications. So, and I will just point out that there are some very nice review articles. So if you would be interested to know about this more, if you find the talk interesting, then you can look at these very nice review papers. Okay, so now I will briefly talk about the gravitational heating and cooling mechanisms that will be of interest to us in this talk. So first of all, let's think of a smooth potential. So we can think of the dark matter halo of the Milky Way without any substructure, without any mergers going on, just a smooth potential. So in this smooth potential, if we place something at a particular radius in a circular orbit, it's going to stay in that circular orbit, right? So that is what is shown with this black line here. So in a smooth Milky Way potential, a particle was placed in a circular orbit, and you just see that the particle maintains its orbit at 8 kiloparsec. But now if we add substructure to this halo, so we have clumps, and these clumps are the subhalos that are moving around in the Milky Way halo. So what will happen is that the orbit of this particle is going to be perturbed because of its interactions with these clumps. So in a clumpy potential, the orbit of a test particle, that is going to be perturbed by gravitational encounters. And if this process is dominated by many weak encounters with the clumps, then it is a diffusive process. So by which I mean that if we think about an ensemble of particles, then the change in energy over time of this ensemble, that can be written as a diffusion equation. So this is the diffusion equation. So this is the change in energy per unit time of an ensemble, and it is given by these diffusion coefficients. So this is called the first order diffusion coefficient, and these are the second order diffusion coefficients. So this term, the first order diffusion coefficient, that is actually a drag term. So this tries to cool the system. So whereas these are the heating terms. So these would be responsible for increasing the energy of that ensemble. So this term will try to drain the energy, whereas this term, that will try to increase the energy. So that is what you see here, that on an average, so this is always getting perturbed, but on an average, since it's a test particle, so on an average, there is transfer of energy from the clumps to the test particle, and therefore on an average, the test particle keeps moving out. And just to mention that via this mechanism, the Milky Way substructure, it can perturb the orbits of globular clusters, and it can lead to the thickening of stellar streams and also the thickening of the Milky Way disk. Yeah. So the energy is being transferred from the subhalos. Because to the paria, because the background is smooth, it's a smooth potential. On top of that, you have these subhalos. So from the subhalos, the energy is being transferred. So now, if it's not a test particles, so until now we are thinking of a test particle, right? So what happens if it's not a test particle? So now if we have a massive particle which is moving in this same potential, then what will happen is that the massive particle will perturb the overall gravitational potential of the system, And what happens is that introduces a response density, and that response density causes a back reaction on the massive object. And this back reaction tends to slow the massive object down. So this is what we call as the force of dynamical friction. So that is illustrated here. So you have a massive object. This is just shown at one instant of time. And what this massive object does is that it creates an over density and an under density. So that is the wake that is formed behind this massive object. So here is the over density, and here is the under density. And this wake is now pulling this particle in the opposite direction, and therefore it is slowing down. And you see the orbit of the particle that is decaying over time. Right? So the particle started from this position, and since the massive object, this wake is always forming, this wake is pulling the particle behind, and therefore it is slowing down as it is moving. So this is the force of dynamical friction, right? And that is another cooling term. So therefore, if we think about the diffusion picture again, in this diffusion picture, you still have the same heating terms, they are still there, but now there is an additional cooling term. So this term was already there. So now I have an additional term, which is the dynamical friction. So if the particle is massless, if it's a test particle, then this term will not be there. There will be no dynamical friction. But if it's a massive particle, then I have an additional term. And so I have a net cooling that is happening. So therefore, there is this net cooling and there is a net heating. Now, why did I talk about these mechanisms? Because the effect of these heating and cooling mechanisms on baryonic objects that can inform us about the underlying dark matter distribution, because these diffusion coefficients, they depend on the density. So it's happening. So all the heating and cooling, that is all because of the interaction with these clumps. And therefore, it will depend on how these clumps are distributed. So it depends on the density profile of these clumps. It depends on the velocity distribution of the clumps. It depends on the mass of these clumps. So therefore, these heating and cooling mechanisms, their effect on baryonic objects, that can inform us about the underlying matter distribution. So now, moving on with fuzzy dark matter. So let me start by showing you results from a cosmological fuzzy dark matter simulation. So I'm showing you results from the first cosmological fuzzy dark matter simulation that was run. And what you see here is a comparison between fuzzy dark matter and cold dark matter. So this is fuzzy dark matter, this is cold dark matter. So here we see it on large scales. So on large scales, there isn't any difference. So statistically speaking, fuzzy dark matter is the same as cold dark matter. And the boson mass for this particular fuzzy dark matter simulation is 8 times 10 to the minus 23 electron volt. However, when you zoom in, so these are the halos, right? So these are the filaments and these are the halos in fuzzy dark matter as well as cold dark matter. But now, if we zoom into one of the fuzzy dark matter halos, that is what is being done here. Now you start seeing differences from cold dark matter. Yeah. Right. Particle mass, yes. Oh, it's necessary to be a boson because otherwise you can't have. So from the uncertainty principle, it has to be a, like from the Pauli exclusion principle, because for it to behave as a wave, you need to have many particles inside the de Broglie wavelength, and that can only happen if it's a boson. For a fermion, that will not happen because of the Pauli exclusion principle. You can't have more than one fermion in one state.
There is not clear that what's the consequence.
Right.
Generally, the interaction, the gauge particle.
Right, the gauge particle, interaction particles are bosons. Yeah. Yeah. Right. They are the right. Yes. The particle itself, the dark matter particle, yeah, it has to be a nature. Yeah, it has to be a boson. Otherwise, you will not have the wave nature. Right. So now, if we zoom in to one of these halos, now we start seeing differences. Right. So we see that there are interference patterns within this halo. So in a cold dark matter halo, you wouldn't see this kind of structure. So what you're seeing here is interference patterns between the different quantum states. So that leads to all this substructure within the fuzzy dark matter halo. And then if you zoom in further, then you see that there is a pronounced core in the center of the fuzzy dark matter halo, as opposed to a cold dark matter halo where you would have a cusp if you're thinking about dark matter only simulations. And these are, by the way, dark matter only simulations without any baryons. And these simulations are run with this code called Gamer. So Gamer is a very nice code. So it uses adaptive mesh refinement to solve the Schrodinger. So solving the Schrodinger equation is very hard. And for a long time, people who were working on fuzzy dark matter, they were just doing analytical theory, and simulations came in only. So this is the first study was done in 2014, where fuzzy dark matter simulations were possible, and it was possible because of this code, which is heavily parallelized. It uses adaptive mesh refinement, uses GPUs and everything to solve the Schrodinger equation. So I also use the same code in my work. And what I do is that I go to the Redshift 0 snapshot of. So I go to the Redshift 0 snapshot of this simulation that I was showing you, and I pick one of the halos from this simulation. Right? So it's a dwarf mass halo. So it has a virial mass of 6.6 times 10 to the 9 solar masses. And just to remind ourselves that this is the boson mass. And now this halo is re-simulated in isolation, meaning that there is nothing else. We are just simulating an isolated halo in a box. There's some boundary condition. And we simulate this at a fixed spatial resolution of about 100 parsecs. So we see that, the simulation, right? So we take, right. Yes, it's also zooming, right. Well, you can take any snapshot, but we just wanted to take, so normally when people do idealized simulations, you're not taking into account the redshift evolution, right? So you can take any snapshot, but so we just pick the redshift 0 snapshot. Right. So you see that this halo that has many interesting features, right? So you see that there is this central object here, and that is sort of moving around. So this central object, this is called the soliton. So this is the ground state of the Schrodinger equation. And then surrounding this soliton or the ground state, there are the excited states. So you see this entire envelope surrounding the soliton that is made up of the excited states of the Schrodinger equation. And these excited states, they interfere with one another. And because they interfere, it leads to all these underdensities and overdensities. So you see these interference patterns that happens because of this interference between the excited states. And the excited states also interfere with the soliton, and I'll show you more. So what is plotted here is the projected density. So mod chi square is the 3D density. So MB times mod chi square, that is the 3D density. So I'm taking one particular projection. So I'm showing the projected density. This is there. So the movie time is evolving.
It's not changing the density profile.
Because it's a ideal. So because we are taking so we take the halo from the cosmological simulation, and then it's just simulated in isolation. So an isolated halo overall would not evolve. So energy is conserved. Momentum is conserved, everything is conserved. So overall, there will be no evolution in density profile. Like so it will not grow, right? Because it will not collapse. No, it will not collapse. It will not grow.
Time and you are, let's say, evolving in time.
Right. The evolving in time. Yes, there is no redshift evolution. So it's a idealized simulation. So we call these idealized simulations. So you do it in cold dark matter also. You do idealized simulations in cold dark matter also, where you have a cold dark matter halo, and maybe you're interested in dynamical friction. So if you're interested in dynamical friction,
Gravitational collapse.
no, I'm not looking at the gravitational collapse. No. Right, 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 right. 8, about 8, 10 gigayears. Yeah, yeah. Yeah, that's the age of the universe. Yeah, that's the age of the universe. Yeah, age of the universe. Yeah.
And then you look at its
Time evolution. Yeah.
evolution.
No.
It's,
Right. So we are interested. Yeah. So we are interested in the internal dynamics. We are interested in the internal dynamics of the halo, of this isolated halo. Yeah. 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 And I mean the dynamics. That's yeah. You simulate it for 10 gigayears, but if you simulate it for maybe 2-3 gigayears, also the dynamics is going to be the same. So overall, there is no evolution in the dynamics. Right. So to illustrate better some of the interesting features of this halo, so what is shown in the left panel here is the density profile of this halo at different instants of time, right? So this is rho as a function of r, the 3D density profile, and this is plotted at different instants of time. So that's why you have many curves here, and these curves, they are color coded by the central density, right? So the first thing that you notice is that there's a pronounced core that I already talked about, as opposed to NFW profile would have a cusp. And then you also see these oscillations. So there's these temporal oscillations in the density profile. An NFW halo, if you were to do the same experiment with NFW halo in isolation, it would just stay the same. Nothing would happen. But here you see this temporal oscillations that are happening. And you see that when the density increases, the core decreases in size, and vice versa. So there's a core, there's a relation between the central density and the core. If the density increases, the core shrinks, and the opposite happens. So again, here you see the oscillations in the peak density. So the peak density fluctuates by about a factor of 2. So it's order unity oscillations that happen in the peak density. And what you see below is the power spectrum of these oscillations. So you see that there is a pronounced frequency, and most of the power is in this region. And this frequency is about 2 to 5 gigahertz. So there's actually a relation for that. I haven't shown that, but there we know what would happen if we go to a different fuzzy dark matter halo. It's a well-known. So it depends on the density. So it goes as dynamical time. So this oscillation frequency goes as rho to the power half. If you go to a different halo with a different central density, then the oscillation frequency will change. Why is the oscillation? Why is the oscillation happening? The oscillation is happening because of the interference, right? The ground state that is interacting with the excited states, and that leads to the oscillation in its density. Right, yeah. That's the peak oscillation, yeah. That's the peak oscillation. That's well, this is in right. So this is 1 over gigayear. So to convert that, it is the time scale. It's a time scale. So the frequency can be derived from the basics, from Schrodinger Poisson equation. You can do perturbation theory, and from the perturbation theory, you can derive what would be the expression for this frequency. So it's basically dynamical time. So yeah, right. Mm-hmm. On the dynamical time scale, because of the gravity. So it's a self-gravitating system, right? So there's the gravitational potential, and that is ultimately determining the dynamics of the system. So I think that's the reason, because it's a self-gravitating system, and therefore I think that's the reason why the dynamical time is. So it's not exactly the dynamical time. There is a factor of 2, 3. It's of the order of the dynamical time. Mm-hmm. Mm-hmm. Related to the sound processing time. Yeah, it could be related to say, yeah, I haven't checked that.
The soliton radius is observed
2 kiloparsec, yeah.
and the box size is
Box-
20 kiloparsec.
No, box size is about 30 kiloparsecs. About 30 kiloparsecs.
Boundary condition.
The boundary condition that we used was periodic boundary condition, but we checked with other boundary conditions as well. It doesn't make much difference.
Very small box in the, if you compare with the soliton radius.
No, because we have checked with larger boxes. We have checked with the reason we took this because we were not doing AMR, and there's a yeah, and we want to resolve the dynamics in the central region properly. That's why we went to a 30 kiloparsec box. But we also checked, so 30 kiloparsec. So the virial for reference, the virial radius of this halo is 50 kiloparsec.
That is fine, but we were solved
Right.
that length scale
Yeah.
is not very much
It
larger compared to the
is-
soliton radius.
So the de Broglie, so the soliton size is of the order of the de Broglie wavelength, and that is about 2 kiloparsec. So we have a resolution of about 100 parsec. So we are resolving the de Broglie wavelength in about 20 cells. Yeah, right.
Baryonic soliton radius. That is not very small.
So you are saying that the box size is not very large compared to the soliton radius.
Soliton radius.
So
Because you are interference.
right,
Interference is how it is coming back.
right, Right. right. But we have checked with larger boxes. Yeah, we have checked with larger boxes, and we have statistically seen the same features. So let's say the frequency of the oscillation. So whatever statistics we are interested in, those statistics remain the same. And maybe there could be some edge effects, and at the edges of the box, we may not be getting things correctly. But we would be mainly interested in the central region. So we will, after this, place particles in the center and see what happens to those particles. So for that, we are not really concerned about what is happening at the edges. So we are fine in that sense. Okay, so another interesting feature of this halo that we also saw when we were looking at the movie is that the soliton that actually moves around, right, with respect to the center of mass of the halo. If we take that as a reference frame, then the soliton is actually moving around. And that again is because of the interference of the ground state with the excited states, that this soliton is moving around. And the soliton moves around by a scale which is of the order of its own radius, or again of the order of the de Broglie wavelength. So what you see here are 4 different snapshots. So you see the soliton at 4 different snapshots. And so there's a zoom in a smaller region. So you only see the soliton and somewhat more. And so these white crosshairs, they are the center of mass of the halo. So you see that a soliton position that is clearly offset with respect to the center of mass, and this offset is changing as a function of time, and the offset is about the soliton radius, it's about 2 kiloparsec, or of the order of the de Broglie wavelength. Yeah.
The halo center of mass will be the same as the soliton center of mass.
No.
Because it's the center you are talking.
Yeah, but why would that be the same?
That's why the mass is very.
No, the mass is in the soliton as well as the halo, right? So there is the soliton, and then there is the envelope. So there are 2 things. So the entire halo that consists of the soliton, and also there is the outer envelope, right? So there is the soliton and there is the excited states. So it's not like the mass is entirely in the soliton. So the soliton mass, again, for reference, the soliton mass is about 10 to the 8, whereas the halo mass is 6.6 times 10 to the 9. And this is actually very important, like this motion. Okay, so therefore, we looked at some of the interesting features of a fuzzy dark matter halo. So we know that there are temporal oscillations in a fuzzy dark matter halo. We know that the soliton that moves around with respect to the halo center of mass. And then there are also fluctuations outside the soliton. This envelope, the halo envelope, which is made up of the excited states, there you have fluctuations, right? So these are all sources of heating. So these are 3 different sources of heating. The soliton is a 10 to the 8 solar mass object, which is moving around. Right? It is moving around, and so that is the primary source of heating. Then you also have the soliton oscillation, that is another source of heating. And then you have these fluctuations in the envelope, and you can think of them as quasi-particles similar to sub-halos in a cold dark matter halos. When I was talking about gravitational encounters initially, I was talking about sub-halos. So here you can think of gravitational encounters with the fluctuations, the soliton. The soliton is one big fluctuation, and then there are also other fluctuations throughout the halo. So together, what these heating sources they will do is that if we place something at the center of the soliton, that is not going to stay there, right? And this is, again, if you contrast it with cold dark matter, you place something at the center of a cold dark matter halo, it's going to stay there, right? So why is this important is because of supermassive black holes, because of nuclear star clusters, right? So we think that supermassive black holes are at the center of a halo, or nuclear star clusters by definition are said to be at the center of the halo. But what we find is that in fuzzy dark matter, you cannot have something at the center of the gravitational potential, right? So if you place something there, then it will keep moving out. So all these gravitational potential perturbations, they will keep kicking the particle out. So we have a 10 to the power 5 solar mass particle here. So you see that it was placed at the center of the soliton, and then over time, this particle just keeps moving out. So then, and in the bottom panel, just this motion is shown in different reference frames. So the orange curve and the green curve, they show the motion with respect to the soliton center and the halo center of mass, just because they are not the same. So we show it in two different frames. And then for reference, the motion of the soliton with respect to the halo center of mass, that is also shown with the blue curve. So then the next question is, how long is this motion going to continue, right? How long is this particle going to keep moving out? So that is when dynamical friction becomes important. So depending on how massive the particle is, there is going to be a force of dynamical friction. And that force of dynamical friction is going to slow down the particle. So it's going to oppose these heating mechanisms. So then in a statistical sense, if we start with an ensemble of particles, then this ensemble will keep moving out until and unless these two opposing forces are able to balance each other. So that is what we do next. So we look at statistical properties of ensembles of different masses. So starting from 10 to the power 5 to 10 to the power 6, 5 times 10 to the power 6 and 10 to the power 7 solar mass particles. So different panels correspond to different masses. And what we do is that in each panel, we have an ensemble of about 50 particles. And we always start them from the center of the soliton, and then we let them evolve. So what we do is that we place the particle at different instants of time. So because we have only one halo, right? So what we do in order to create this ensemble is that over a 2 gigayear time span, we place the particles at different instants of time. And statistically, the motions are going to be somewhat different. And then what we look at is how is the mean radius of this, or like the mean change from its initial position. So the mean distance, how is that changing? And what is the 1 sigma variation in that distance? So those are the different envelopes, like the solid lines, they show you the mean, and the envelopes, they show you the 1 sigma variation over these ensembles. And then in each panel, what you also see are cyan curves, right? So there are the colored curves, which are different masses, and then there are also the cyan curves. The cyan curves are for massless particles. So we put exactly 0 mass particles and see what happens to them, right? So you can see that 10 to the power 5 and 10 to the power 6 solar mass particles, they basically behave as massless particles. So statistically, there is no difference between massless particles and these two masses. That is because dynamical friction on these particles, that becomes important at much later radii. Because of the smaller mass, dynamical friction will become important at much larger radii, much larger distances, and we just don't reach those distances within our runtime. So we run these simulations for 20 gigayear, we are just not there yet. So we don't see the effect of dynamical friction. But as we go to more massive particles, we start seeing the effect of dynamical friction. So you see for 5 times 10 to the 6, there is reduced outward diffusion as opposed to massless particles. And then when we go to 10 to the 7 solar mass particles, now we start seeing this balance that I was talking about. The heating and the cooling, they're trying to balance each other. And in a net sense, the ensemble is not evolving anymore. So it's somewhat stalling. That is what we call stalling. Okay, so the motion of different mass particles in fuzzy dark matter halos, so motions of star clusters of black holes in fuzzy dark matter halos, that has been studied before our work. It has been studied using analytic formalisms, using this diffusion picture that I introduced previously, using the diffusion coefficients. That formalism is valid only when we are thinking about the interactions of the particle with the envelope beyond the soliton. So the quasi-particles, so the fluctuations that exist in the envelope, there you can think of that the interaction of the particle that is being dominated by many weak encounters, because these quasi-particle masses are small. So there the diffusion picture is valid, and this analytical formalism can be applied. But if you're interested in the motion of the particle near the soliton or within the soliton, then we cannot really apply this diffusion approach, because here the motion is dominated by interactions with one massive soliton. So you need these simulations. Yeah, good.
These phase particles, they are point-like particles.
Yeah, point-like particles. Yes, we are not taking into account the structure of the part. Yeah, we are not taking into account the structure.
How can we do that? It should be larger in size. I'm not talking about structure.
What should be larger in size?
The particle size. That if you are talking about this is star cluster,
Mhm.
2% solar mass shape.
Yeah, well, it's a star cluster is like 5-10 parsecs in size.
Larger. So when you are talking about this analytical fiction kind of thing,
Right.
it's affected by the surface stuff as well.
Somewhat.
Surface is important rather than a point like
It depends on how compact or the object is. If it's
it is 20% solar mass and your total size is 21.9.
the total halo mass.
Total halo mass is
Yeah.
21.9.
Right, but if it's a 10 to the 7 solar mass particle, which is very compact, then the dynamical friction or 10 to the 7 solar mass point particle, as opposed to a 10 to the 7 solar mass particle, which has like 5 parsec or 10 parsec size, it's not going to be very different. We have actually studied this in a different context, like in a different study, we actually studied this. And yeah, I agree with you that if that 10 to the 7 solar mass particle is much larger in size, if it's more diffuse, then yes, then it's not applicable to be treated as a point particle. Yeah,
Compact.
right.
That may not be the your dark matter.
So, but star clusters don't have dark matter. That's the common,
Don't have the term,
right?
but the general dark matter will be there.
Right. Yeah.
That is the biggest object.
So you're saying the dark matter in the star cluster,
Yes, that's massive thing.
the halo,
Big of the star cluster.
but the star clusters don't have a halo.
Within that cluster,
Yeah, it's not. Yeah, it's not gravitationally bound. Yeah.
dark matter is
Well, okay. Yeah.
matter is
Yeah.
that is going to be there.
Yeah.
Your point particle in mass and what you are using.
Right.
Subtract that.
Right.
That
So that dark matter is the same as the dark matter in the halo. If it's not bound, then that's the yeah. So the drag that will happen, that's what I'm saying. So I agree with you that if that 10 to the 7 solar mass particle is somewhat diffuse, then that drag will be different. But if it's sufficiently compact, then
how can you model this compact dark matter will be there? This compact dark matter particle. This particle is the dark matter particle.
well, the test particles that we put, they are not dark matter particles. The test particles are thought of to be black holes or star clusters. So we are seeing what would happen to them in a dark matter halo. Yeah. If it's a black hole, then the size is irrelevant. It doesn't matter. And if it's a star cluster, then the size will matter at some point. Like if the star cluster is sufficiently large, then yes, the size will matter. But yeah, we are not taking that into account. So we are implicitly assuming that the star cluster is sufficiently small so that that is not a consideration.
What is the reach of the particles which will bring back over here?
Right. It will move around, and in an on an average, it will keep moving out. So its average distance from the, so it will, right. So how far, that depends on the mass of the particle. If it's a massless particle, then it will just keep moving out because there is no opposing force. On a massless particle, there is no dynamical friction. So if you put a massless particle, its average separation from the soliton is just going to keep increasing, just going to go out and out. But if it's a massive particle, then at some point, dynamical friction will become important. When it becomes important, that depends on the mass of the particle. And if it's more massive, then it becomes important at closer to the soliton. Right? So that's why you see stalling for more massive particles. And if it's less massive, then it becomes important at much later radii. So it can travel to larger distances if it's less massive. And that's the reason why you don't see dynamical friction for the more less massive particles. Now, if you want the exact relation, that if you want a mathematical relation, then that needs to be worked out. So that can be worked out using the diffusion coefficient approach that I talked about previously. Using that, you can work out the mathematical equation that will tell you that, okay, if this is the mass of the particle, if this is the mass of my quasi-particles, then this is the radius up to which it is going to diffuse on an average. But then that is what I was trying to point out here, that those equations, analytical formalism, they are only valid for interactions of this test particle with the clumps of the quasi-particles outside the soliton. So within the soliton, all these analytical formalisms no longer work because it's this one big soliton which is interacting with the particle, and which is why we need this kind of simulations. So I think I'm running out of time. So how long should I continue? 10 minutes, okay. Yeah. So why are these simulations important, or what can we do? So now we know this result that if we have nuclear objects, then these nuclear objects, black holes or star clusters, they cannot be at the gravitational potential center in a fuzzy dark matter halo. So then what do we do with that? So we can now then look at observations. So what do we find in observations? Are star clusters or black holes exactly at the center of halos in observations? So that's why I'm showing two recent results, two recent studies. One is of black holes in dwarf galaxies, that is on the left. So here I'm showing 4 different galaxies from a sample by Rains et al. 2020. So these black holes are detected in radio. So that is what you see with the red crosshairs. And you see the optical image of the galaxy in the background. So you see that actually black holes in dwarf galaxies, these are all dwarf galaxies. So black holes in dwarf galaxies can actually be offset from the center of the galaxy. So here I'm showing you 4 galaxies, but in this particular sample, what the authors say is that most of the galaxies have off-centered black holes. And another study that I'm showing is of nuclear star clusters in a sample of dwarf galaxies in the outskirts of the Virgo cluster. Here also, you see that, so what is plotted on the y-axis is the offset. So the distance from the center of the galaxy of this nuclear star cluster as a function of surface brightness, and then again as a function of surface, it doesn't matter. It's just a collection of star clusters. And what is plotted is their distance from the center of the galaxy. So again, you see that nuclear star clusters can actually have significant offsets. So previously, it used to be thought that nuclear star clusters are nuclear. They are at the center. And it is also commonly assumed that black holes are at the center of galaxies. In cosmological simulations, still people, when they seed black holes, then normally in cosmological simulations, the black hole is always seeded at the center of the galaxy. But in observations, what now recent observations are telling us is that black holes and nuclear star clusters, they may not actually be at the center of the galaxy. And whether this is because of fuzzy dark matter or whether there is some, so it can happen in cold dark matter also. There have been studies that have been shown that offsets of black holes can happen in cold dark matter because of mergers. So when you have two galaxies merging together, the smaller galaxy, it gets stripped, its black hole remains behind. So now you have a larger galaxy, a smaller galaxy merged with a large galaxy, the small galaxy stripped away, the black hole remained behind. So now you have an offset black hole in the larger galaxy. So that is how you could get these kind of offsets in cold dark matter. But in fuzzy dark matter, there's a natural way also to get these offsets. So therefore, if we want to use these offsets to predict the fuzzy dark matter, so to put some constraints. So ultimately, what we want to do is that we want to use these observations to put a constraint on the fuzzy dark matter particle mass. And what I have been showing you are results for one particular fuzzy dark matter particle mass, one particular halo. So what we want to be able to do is that we want to be able to make these predictions for a whole bunch of dark matter halo masses and fuzzy dark matter particle masses. And these offsets are going to be a function of those two quantities, right? So if you decrease the fuzzy dark matter particle mass, then the quantum nature becomes more quantum, and everything increases, heating increases. So if you decrease the fuzzy dark matter particle mass, then these offsets will increase. And oppositely, if you increase, so as you go to higher fuzzy dark matter particle masses, these offsets are going to decrease. So therefore, using the observations, you can put constraints on the fuzzy dark matter particle mass. And that requires us to expand our study, which we will do in the future using simulations as well as semi-analytical modeling, because running simulations for every halo mass, every boson mass is not feasible. So we have been working on semi-analytical models and using a few simulations, calibrate these models, and then use these models to make predictions for a large number of, explore the parameter space more easily. So maybe I'll skip. Maybe I'll just show one slide and then I'll stop. So another way that we could, I was talking about nuclear objects, so star clusters and black holes. The other interesting thing are dwarf galaxies themselves. Can we get some constraints using dwarf galaxies themselves? Right? Because all the problems in dark matter, they started with dwarf galaxies. It all started with the missing satellites problem. And so dwarf galaxies are very important because they are dark matter dominated objects and they can tell us a lot about dark matter. And so we also looked at what happens to dwarf galaxies in fuzzy dark matter halos. So, and you might already guess what would happen, because if point objects keep moving out, then now if I have a collection, now if I have a profile, so my dwarf galaxy is basically a profile of many stars. So something like what we were talking about, a diffuse star cluster, something much more diffuse, a galaxy. So if I now place this galaxy in a fuzzy dark matter halo, then this galaxy keeps expanding, right? Because of these heating mechanisms, the galaxy keeps expanding over time. So then we can also think about using galaxy sizes, right? The profile, the morphology of galaxies. I will not talk about all this. I'll just show this and stop. This is another interesting, so you can use sizes. You can also use morphologies. So galaxies are not always spherical. We have spherical galaxies, we have elliptical galaxies. So what we are doing here is that we simulate the evolution of a spherical galaxy in a fuzzy dark matter halo. And then we also simulate the evolution of an elliptical galaxy in a fuzzy dark matter halo. So we start with the ellipse, right? So initially that's a sphere. So that panel there is the initial condition. So start with the sphere there. You start with the ellipse here. But over time, you see, again, these heating processes that are happening, they tend to isotropize the galaxy. So what happens is that this ellipse is gradually getting converted to a sphere, right? So in the end, there is not much difference between these three panels and these three panels. So then one of the predictions would be that depending on the fuzzy dark matter particle mass, it would be hard to have old elliptical galaxies. If a fuzzy dark matter particle mass is too small, then you will not have old elliptical galaxies in the universe. That's just simply not true. There are old elliptical galaxies. So therefore, that's another way in which you can put constraints on the fuzzy dark matter particle mass. And another thing that maybe not so apparent is offsets between isopers. So these are the isopors of the galaxies. So you see that we start with a concentric galaxy, right? By construction, it's spherical galaxy with concentric isopors. But as it evolves, you see that the isopors are no longer concentric. There are significant offsets between the centers of one isopod as opposed to another isopod. So isoportal offsets is another quantity that can be used. And so I will stop here, I think. So I had some slides in the modeling, but I will not go there. So I'll stop here with the message that fuzzy dark matter is an interesting model and more work needs to be done and to see whether it's actually a viable model or not. And we will be working on that in the future. And so stay tuned.
So first question I have regarding that, you told about you studied the dynamics of equation of state also as if in the initial slide you talked about. So can you state for this fuzzy dark matter what would be the my omega, this was the equation of state?
Well, so the equation of state, yeah, that was something I just I was not really talking about the equation of state. What I meant was the Schrodinger equation. So the dynamics.
That dynamics, can you say something on the equation of state of the dark matter for this fuzzy one?
Yeah, I have to think about that. If you can say something about, pressure versus density. Yeah, you can work out the sound speed. So it's basically sound speed square by right. So you can work it out, but off the top of my head I don't know what the answer for that is.
I have another question. So you use this Schrodinger equation and we talk about the wave nature of the particle, and that's when you took the wave equation.
Right.
But in some times you talk of the bosonic mass, and in the last slide you said less the mass we decrease, the quantum nature effects
right.
will be more relevant.
Right.
So even when we go for the particles, when we talk of particle, is it duality?
There's a duality, yeah.
Yeah. So does Schrodinger equation works in every regime, or that also needs some modification for working throughout all this thing of for dark matter? I mean, always that equation works, or do you need any modification? Because
so that is something related to what you were saying, that if you decrease the mass too much, then whether relativistic effects become important or not. So if relativistic are important, then you need to go to Klein-Gordon.
Exactly.
Need to go to Klein-Gordon and Poisson equation. So I have to think about that. We have been, so normally the masses that we think about is 10 to the minus 23 or maybe minus 22 to minus 19 electron volts. In that regime, I think you don't need to go to relativistic. You can always do it with Schrodinger Poisson equation.
Thank you for the answer.
Nice job, Dhruba. So my question is, I was just wondering, how did you isolate the halo from the simulation? Like, what are the boundary conditions you put?
Right.
Not see the evolution of that halo with the time evolution.
Right. So basically, what we do is that so you have the whole snapshot of the cosmological simulation, and then we just make a cutout. Right. So we know the virial radius of the halo. It's about 50 kiloparsecs. And our fiducial runs, the box size was 30 kiloparsec. So what we do is that centered on the center of mass of the halo, we just make a 30 by 30 by 30 cutout, right? And then this cutout is now my new initial condition, right? So this new initial condition is now simulated for some time with periodic boundary conditions. We adopt periodic boundary condition. Right, so the wave function is, the boundary condition on the wave function is periodic, but we also check with, say, if you make the wave function 0 at the edges of the wall, that's called rigid boundary condition. So we check with both rigid and periodic boundary condition. Doesn't make much difference in terms of the statistics. Maybe there are some differences towards the edge of the box, like maybe between 25 to 30, I don't know, that SSR was saying. But in the central region, it doesn't make much difference statistically.
And another question is, why did you choose this dwarf?
Yeah, that is because dwarf galaxies are what. Oh, so one reason. So in fuzzy dark matter, all these effects go down as you increase the halo mass. So if you go to higher halo masses, then from relations that have been found in cosmological simulations, if you go to higher halo masses, then the soliton size decreases, or the de Broglie wavelength that decreases. So for a given boson mass, if you increase the halo mass, then the de Broglie wavelength decreases. That's just because de Broglie wavelength goes as h over mv. So you increase the v as you go to higher halo masses. So de Broglie wavelength decreases, and so these quantum effects will be much less. So for the same boson mass, we don't expect to see this kind of soliton wobbling in the Milky Way. So we do expect to see some wobbling, but for the Milky Way soliton, if there is a Milky Way soliton, then the wobbling is going to be much less as opposed to the soliton in, say, a dwarf galaxy like Tucana or Eridanus 2. So therefore, we wanted to start with dwarf galaxy because that is where you would see the most of the signature. That is where you would get the best constraints.
Thank you.
Any other questions from the audience? Okay, this is
So, you are choosing some boson mass. That is one parameter you are choosing. What about your other coefficient, diffusion coefficients and things like that? Those are
That is all included.
specify the mass.
Yeah, if I specify that boson mass, then everything will differ. Yeah, because I mean, in the simulation, it's all happening self-consistently. But if you want to make analytical theory, then in analytical theory, the only free parameter is the boson mass and the halo mass. So halo mass will give you, yeah, everything, yeah,
is
related to the halo mass and the boson. Yeah.
And so that's not only one thing.
Right. There's only one. Yeah. There's only one parameter. Yeah.
And about the offset thing. So also the initial perturbation mass. How much is the initial bosonic mass?
The particle mass of the mass of the boson particle, the dark matter particle.
The code is using
Right.
that is that length. Okay, length scale you are already fixed by
the boson mass. Yeah, the boson mass fixes the length scale. Yeah, the length scale is basically de Broglie wavelength. Yeah, that's the length. That the same length scale throughout the halo.
any other questions? Yes.
Okay, thanks for the nice talk. So I just have a question that you throw assume that a halo, like you're seeing halo as an isolated system. It's not interactive, but like the physical equations that there are many halos and they should interact. So if we like include that interaction, how should they change much like on what basis are we making this interact?
Because always start with simple things and then you build on complexity. So these are the things that being done for the first time. No one before this has actually looked at the kind of studies that I'm looking at. So therefore, we wanted to start simple. So we start with isolated simulations. You look at what happens here, and then you gradually build complexities. At the present moment, there are very few cosmological fuzzy dark matter simulations. The ones that are there, they're also very small box simulations with like few halos, like maybe 20, 30 of the order halos, and with not much high resolution. So we were interested in the internal dynamics of the halo, because to see what happens to these point objects, what happens to galaxies, you need high resolution. And for that high resolution, we need to have isolated halo where we can achieve this high resolution in a like reasonable amount of time. But yes, I agree with you that we are missing a lot of physics. And to include that, we will have to go to cosmological simulations, and that is all in the pipeline.
Okay, thank you. So just ask my question only. I was also about to ask that what is the situation if two fuzzy dark matter
Halos would merge, yeah, right.
in general case, we know that they pass by each other. Just the situation for cold dark matter.
Oh, no, in fuzzy dark matter, they will not
What will
pass by.
happen in that case?
In fuzzy dark matter, they won't pass by each other. There is going to be interact because of the quantum nature. The wave function of one is going to interact with the wave function of other, and then you will have interference. So then you will have.
And that interaction situation, that is some sort of in the quantum scale only we are talking about. Would that create some disturbances in the surrounding nature, like causing some sort of gravitational wave or that kind of signature that might possibly be able to observe by us?
Maybe, yeah, I don't know. That's a good question, yeah. If that leads to some kind of, yeah, gravitational wave signature from there, like black hole mergers. You
The
think,
black hole merger gravitational signatures are quite detectable ones, the ones we
Yeah.
really detected, but these
Yeah.
situations, I think that we have much fainter ones. So will that be able to detect it, or that will just add up to the stochastic nature background?
yeah, I don't know the answer to that.
Any other questions? If not, then I have a couple of questions. So the first one is, so let me see your motivation. So as you said that CDM has these problems, like you have the missing satellite problem, you have the forecast problem. Although within the CDM paradigm, we try to solve those problems, as you said. I think to me, CDM seems little bit, CDM seems problematic from another point of view because it's unphysical. I mean, because CDM, there is no interact. So when we assume CDM, there is no self-interaction. Now that's impossible. I mean, in nature, in physical reality, it's an absurd model. So there must be some interaction. That part, of course, we need to correct for CDM. But then, are you trying to tell us that we should abandon
No.
CDM completely
No.
and then have empty?
No,
Or is it like a mixture that maybe because CDM paradigm has been super successful in describing.
I'm not saying that we should abandon CDM and believe that FDM is the correct model. I haven't even shown you the constraints on FDM mass that we get from my studies. So I don't know what maybe the constraint that there have been others. So I can actually show a table.
So then the point is that why should we bother about FDM? I mean, is it like
Well, then why are we bothering about self-interacting dark matter? I mean,
yes, so that part I think I agree that maybe when we talk about fuzzy dark matter or SIDM, then the issue is that we're not abandoning CDM.
we are not abandoning
completely.
CDM, no, but we are.
Trying to. So, for example, people talk about warm dark matter.
It is, I think, a very small mass range that is still not constrained.
Forecast.
Yeah.
So, are we to, so from the top what we heard today, let's say SIDM or things like that, are we to take the message that yes, CDM is super successful, and since we do not know anything,
Since we don't know anything about,
nature of dark
we should just keep exploring.
yeah, we should keep exploring, and but it doesn't mean that.
Yeah, that doesn't that doesn't mean.
So then my question comes, I think it's related to one of the questions. That is, suppose I look at matter power spectrum. So what effect? So because if you have just fuzzy dark matter, then we not because you showed in one of the simulations.
So you're talking about the CMB.
Yeah, CMB or CMB or the matter power spectrum, as we see, like if you
Right.
look at Galaxies, if you look
Right.
at slow measurement.
Right.
So
Right. So right, there are constraints from CMB as well as from Galaxy. Yeah, I think from clustering of galaxies also in Sloan. Those constraints are about. So those are not very they're very liberal constraints. So from CMB, I think the constraint is about 10 to the minus 24 electron volts. So that's so anything below 10 to the minus 24 is ruled out. So it has to be above 10 to the minus 24. So CMB is not very constraining. Like the galaxy clustering is also not very constrained. There also you get a constraint to minus 23, minus 24, something like that. So CMB will be more constraining with the next generation of CMB
With
experiments
S4.
with S4. With S4, it is being predicted that CMB will be more constraining, maybe 10 to the minus 22, minus 21. It can rule out that. But I think so. CMB is the only experiment that in the FDM community that is what people trust, because the other ones have lots of uncertainties. Like I can show you a list of constraints that have been obtained with different studies, and many studies say that FDM is completely ruled out. There are many studies that put constraints at 10 to the minus 20, minus 19. There are studies which say anything less than minus 20, 19 is ruled out. Minus 19 is like super constraining. We don't even call it FDM anymore. But there are lots of uncertainties in all these studies.
Okay, so then maybe the last A-B part question. The first is, if we are thinking about ultralight dark matter, it's always occurred to my head. Then if you think about their free streaming state, you were talking about wave interference. But if you look at the evolution, if you look at early universe, and let's say we have ultralight dark matter, then decoupling. So if I think of CDM, and they are super heavy matter, and
Right.
They just
Right.
decouple from your
Right.
thermal equilibrium
Right.
much before. I mean,
Right.
in the very early phase.
Right.
That ultralight dark matter.
Right.
Do you think that they should still be in thermal equilibrium for a longer time?
I don't think so, because the origin of this is not thermal. So
This is non-thermal.
this is non-thermal origin dark matter. So it still decouples at the same. Yeah. Yeah, I don't even care. Yeah.
It's not.
Yeah. So it's not in thermal. Yeah. So it's non-thermal. It's non-thermal dark matter.
And then should that not have any, should it have any effect on, let's say, things like, so it will not have effect on BBN or anything like that? Oh, but this is only gravitationally they are.
Yeah, they're still gravitationally interacting. Yeah, there is no other. There is self-interacting fuzzy dark matter.
Yes, so
You can turn on a self-interacting term, and not much work has been done with that, but it is possible to have self-interacting fuzzy dark matter also.
Okay. So then what are we supposed to do? I mean, so I run a simulation. I want to match large scale structure. What am I supposed to do? Should I run a full CDM simulation, or should I mix it with FDM? What is your take on it? I mean, how do you think of structure formation? And I understand that since we do not know anything about dark matter, we're completely in dark about dark matter, and that's why we
are exploring. We are trying different things.
I have to move on it, right? So what should I do? Should I put fuzzy dark?
People have tried that. There have been studies that have looked at combinations of fuzzy dark matter and cold dark matter. You have some percentage of fuzzy dark matter, some percentage of cold dark matter. There have been studies like that also. I think there's just different people are trying.
So maybe okay, this is dark matter. Definitely that doesn't interact electromagnetically.
Yeah.
They must have some kind of self-interaction. Let's try to find out that what could be the alternatives, all the models that we can explore given the core of observation and results.
Right.
That could take.
Yeah.
So maybe if there aren't any other questions, we can stop here. We had, I think, series of questions, probably at the level of Shakrata's talk, the first talk.
I was not able. Yeah, I had a lot more slides, but that's okay. Yeah, that's fine. Yeah, we had lots of discussion. Yeah, we had lots of discussion.
Let's go and for coming just like 1 day before the break, and I hope we'll meet again for the super success, a very interactive colloquium session. So let me advertise the next colloquium right away. Who actually did this PhD with Frank and God? It turns out that one of Frank's probably first.
Maybe not first, but yeah, one of the first. Yeah.
I don't remember at Alita. The student is visiting presidency, and the next talk that is supposed to be on 12th October will be given by Sudhir More. I haven't seen the topic yet, but it will probably be something related to gravitational. So we have one more cosmology block, and both thanks to them, back to that for the day. Okay, thank you so much. Dhruba.
Yeah, thanks everyone.
Let's now stop the recording.